Today we shall study in this lecture a simple harmonic oscillator and a damped harmonic oscillator. Let us consider that a block of mass m is connected to one end of a spring and the other end of the spring is fixed at a rigid support, and the block rests on a frictionless surface. Let us suppose that this O is the position of the block in equilibrium situation. If we pull the block up to a certain distance xm in the positive x direction, and if we after pulling it, if we just release it, it will move along this direction, and there will be a repeated motion. Okay, it will come up to this minus xm, and then it will repeat. So this will be a periodic motion, and this kind of motion is a simple harmonic motion. We assume that the surface is friction. Surface is frictionless. Now this motion of the block is simple harmonic motion. The body that executes this simple harmonic motion is known as a simple harmonic oscillator. Now there are some characteristics of simple harmonic motion. What are these? The motion should be linear. And the motion should be to and fro motion. Third is periodic motion. And fourth is force is proportional to minus x, where the negative sign indicates that the force and displacement are oppositely directed. Okay, from the fourth property, if we put equal sign, then we'll have to put a constant k, where k is the proportionality constant, known as the spring constant. We know force is mass into acceleration, and acceleration is the second derivative of position. Okay, so you see this the simple differential equation of the simple harmonic oscillator. Okay, if we divide both sides of equation 2 by m, then we'll have now if we put this k by m equal to omega, then we have k by m is omega square. This is equation number 3. Okay, the solution of 3 is a second order differential equation, so there are two solutions. Okay, these two solutions we can write down e to the power I omega t, and another e to the power minus I omega t. So the general solution is this equation 4 can be rewritten okay, so this is the solution of the differential equation for simple harmonic oscillator, where omega is square root of k by m is known as the angular frequency, which can be written as twice pi f. F is the frequency, xm is known as the amplitude, and phi is known as phase constant. If we differentiate equation 5 with respect to time t, then we'll get the velocity. Okay, so we have this solution x as a function of time, xm cos omega t plus phi. Therefore, the velocity we differentiate x with respect to time, then we get this. Okay, if you say this is equation 6. Now the force field acting on the simple harmonic oscillator is the conservative force field. Thus the force can be written as the negative gradient of the potential energy of the spring. If U of x is the potential energy, then the force acting on the block spring system is negative of the gradient of the potential energy. And this one gives us after integrating with respect to x, we get u as a function of x equal to half k x square. So you see this is equation 7. This is the potential energy. Now the kinetic energy T equal to half mv square and V was minus omega xm sine omega t plus phi this squared. This one we have used this equation 6, this the velocity. Now this m omega square equal to k, because omega is square root of k by m. So if you square both sides, then m omega square becomes k. We put here, and this xm square, this one is 1 minus cos square, and which can be written as u of x. So we can write down the kinetic energy as a function of x and this. Therefore, the total energy E is T plus u, and if you add this 7 and 8, you will get half k xm square. This is equation number 9. So we get in terms of positions. Position X, kinetic energy is, you see this is, you can write down this one or this one. And potential energy and total energy. Now you see, if you add this T and U, you will get this. Okay, this is equation, say, number 10 together. If we plot this, um, if this one is, say, xm and this is minus xm, then you see this is u of x, the potential energy. When you see this expression of u as, you see this one, so this is potential energy. And kinetic energy, this is half k xm square, so this point is xm square. And so if you plot this one is kinetic energy. And if you add at any position, you will get the total energy. So this is total energy. So sum of the potential energy and kinetic energy is constant. This is the conservation of energy. In terms of positions, X is satisfied. Conservation of energy is satisfied. Okay, now if we write down those expressions of T, U, and E in terms of time T, so in terms of time T, we have kinetic energy, and it was 1/2 k xm square minus u of x, and which is half k x square. X means xm square cos square. Okay, so, and if you take common 1/2 k xm square, then you have 1 minus cos square. is 1/2 kxm square. This is sine square. Therefore, so we have t equal to this, and u of t is 1/2 kx x square. So and total energy is a constant, which is 1/2 kxm. Or if you add these two, this one and this one, then take common half kxm square, you will have sine square theta plus cos theta, which is 1. This is 11. Now if you want to draw this in terms of time t, and let us see whether the energy conservation is satisfied or not. This is t. Let phi equal to 0, and if phi equal to 0, then if you plot t, then t equal to 0, so is sine 0 means 0, so you have this like this. And cos, if you plot this one u and t equal to 0, then this is maximum. This is the total energy. It will be like this. Okay, and this one is in the t, the kinetic energy, and this one is potential energy. And you see the sum of this u and t is constant, which is E is 1/2 kxm square. So what we have seen in terms of position as well as in terms of time t, graphically we have shown that the conservation of total mechanical energy is satisfied. Next, we shall consider a damped harmonic oscillator. If we draw the figure for a damped harmonic oscillator, it will look like this. So you see, a block of mass m is suspended from a rigid support by a spring, and the one end of the spring is attached to the fixed support, and the other end of the spring is attached to the mass m, and ultimately the mass m rests on a van which is immersed in a liquid with damping constant B. Now, if we somehow displace the van a bit, then what will happen? There will be a harmonic oscillator, and the block will swing up and down inside the up and down, and gradually with time the oscillation will decrease because there is a viscous damping constant in the liquid. Well, there are two forces acting. For simplicity, if we neglect the gravitational force, then we have only two forces acting on the block or the block spring system. For simplicity, we shall neglect the mass of the spring compared to the mass of the block. And these forces are the spring force, which we denote by Fs, which is minus Kx, and 2 the damping force because of the liquid, and which is written usually as minus B into V, where B is the damping constant. So we know that K is the spring constant, and B is known as the damping constant of the liquid. Remember, the liquid is a viscous liquid, therefore there is a damping constant. Okay, now so we can write down the total force. Okay, which can be written as mass into acceleration is second derivative of position with respect to time, and velocity is first derivative of position with respect to time, which can be written as just bringing these two terms on the left hand side. Okay, you see this equation, this is the differential equation for the damped harmonic oscillator. This is a second order differential equation. We can write down this solution. Where phi is the phase constant. Now you see the amplitude of the damped oscillation is so the amplitude actually depends on time t, which is not constant. We shall calculate the potential energy, kinetic energy, and the total energy for the damped harmonic oscillator. To calculate the kinetic energy, we need the velocity, and the velocity is the first derivative of position. If we differentiate x with respect to time t, we'll have this. For a small damping, we can neglect the second term. On the right hand side, compared to the first term. Therefore, approximately we can write down velocities okay, then we can write down the kinetic energy. Therefore, the kinetic energy T is v square half m, and v was minus omega xm to the power minus bt by 2m sine omega t plus phi. So if we square this, then it will be pt by m, and this is sine square omega t plus phi. But if we recall, we had omega angular frequency was k divided by m. So m omega square equal to k. If we use this, then we can write down this. So this is kinetic energy, and potential energy is u, which is half kx square. We know, but x is xm e to the power minus bt by 2m and cos omega t plus phi size whole square. So if we square again, it will be to the minus bt by m, and this is cos square omega t plus phi. This is the potential energy. So if we add this to the potential energy and this kinetic energy, we'll get the total energy of the block spring system. Kinetic energy was half k xm square to the power minus bt by m. It was sine square omega t plus phi, and the potential energy u is half k xm square power minus bt by m, and it is cos square. So if we add these two, we will have this. So you see our total energy, mechanical energy is this. And now you see the total mechanical energy is a function of time t. Now if we recall, we had x is a function of time t, which was xm to the power minus bt by 2m, and it was cos omega t plus phi, and we have total mechanical energy. This is also a function of time, and it is half k xm square to the power minus bt by m. If we plot these two, the displacement of the damped harmonic oscillation and the total energy of the block spring system, then they look like this. I'm now going to draw this. So the displacement for simplicity, let the phase constant is 0. And if we plot the x, this is xm, this is minus xm, so you see when phi equal to 0, so we'll have cos omega t. When t is 0, it is maximum. Cos 0 is maximum. So it's this one is to the power b minus bt by 2m, and this is actually x of t. You see, with time the amplitude decreases because the amplitude now depends on time, this e to the power minus bt by 2m, and it will oscillate because of the term cos. Similarly, the total energy we plot this, and we found that the total energy is e to e of t is half k xm square e to the power minus bt by m. And if we plot this, yes, so it's exponentially decaying. Okay, now we can interpret this result. We know that total mechanical energy must be conserved, but here we see that with time the total mechanical energy decreases. Now where this energy actually goes? This energy goes to generate heat inside the liquid. When the fan moves up and down, there will be generation of heat. So the conservation of total mechanical energy is not violated. Okay, and this is for today, and we are at the end of our chapter 2, and I hope that if you study the class notes that have been supplied to you through the Google Classroom, definitely you will be helpful.